Hello guys, welcome to my channel Engineering Knowledge. In this new lecture, I will discuss how to integrate machine learning models with deep learning models in Python. Do watch the video till end to grasp all the concepts. Let's get started.
Welcome to the new lecture, the course Wireless Research on the channel Engineering Knowledge. Let us start and investigate how we can integrate machine learning models with deep learning models. As a recap of the previous deep learning model that we have seen, the various procedures that we take care of are importing the libraries, importing the data set, which will be features and labels, preprocessing, model definition, compiling and training, prediction, which will be the predicted output, and the evaluation process. I will demonstrate the concept using a basic squaring operation, and then you will, in further lectures, we will do this on wireless communication data sets. So basically, I am taking x1 and x2, two numbers, columns of files. These are my features, and the actual operation is multiplication of x1 and x2, which both are same, so it becomes x square. So y is equal to x square is the actual model. So we'll train the deep learning model with these labels and features to predict based on the understanding of the underlying f of x, which is y square. For that, we import Python libraries like if we import for mathematical operations, we import NumPy as NP, which means whenever we write NP in Python, it represents the complete library of NumPy. For data handling, we use Pandas. We'll import Pandas as PD. From scikit-learn preprocessing, we will perform standard scalar operation. So then we will use TensorFlow.keras.models to use the sequential model. Remember, this is the feed-forward model. And in that, we will use fully connected network, which will be from importing from TensorFlow.keras.layers and as dense layers. We'll also use some plots. So matplotlib will use .pyplot, and I will import it as PLT. So whenever I write PLT in Python, it represents matplotlib.pyplot. The training data set is basically, we'll use a CSV file. Suppose the name of the CSV file is data1 for inference. So the features are x1 and x2. These are numbers from 1 to 200, 1 to 200. And both are equal, x1 and x2. So basically, y is multiplication of x1 and x2, but both are same. So it becomes actually 1 into 1 is 1, 2 into 2 is 4, and similarly like that. So my input data is x1 and x2. My output labels are y, and I am importing these from CSV files. So how do I import from CSV files? I'll use data frames. So like if I want to import all the three, I will show two ways of doing it. So if I want to import all the three columns at once, I will introduce or define a new data frame variable df1, and I will use PD. Remember, PD is representing data frame. So PD dot read underscore CSV. This is my command, and p dot read underscore CSV, and I put the file name, suppose data1.csv. And now I will use columns. I will apply use columns x1, x2, y. So in inverted braces, it is written, which means that these are basically the headers of the file. So if I am writing x1, x2, y, suppose there is also a z here. So it will import only the three, the column A, the column B, the column C, which comprise of the values of x1, x2, and y. But remember, I want features and labels. The features are the first two input variables, while the labels are y. So I will write df2 and read underscore csv data1.csv. This is the file, and use column 0 and 1. Now these zeros and 1 are the indices of the data frame, which means the 0 is the first column, 1 is the second. It is one less, you can understand. So 0 represents x1, while 1 represents x2. And similarly, I want a different data frame variable. So I will declare df3 pd dot read underscore csv to read the file named data1.csv, and I will import 2, which represents the third column, which is y. So I will take df2 values as df2 dot values to be features, and df3 values at df3 dot values as labels. Now, basically, I will try to split the data set and in training and testing dataset. So from scikit-learn dot model underscore selection, I import train test split. So this is the function train underscore test underscore split. And I will give it my input X and Y, which are features and labels from data frames. And it will make it into X underscore train, X underscore test, Y underscore train, and Y underscore test, which means that the features and labels are broken down into X train and Y train and X test and Y test. And this is done in the ratio 0.2, which means 80% of data is taken as X train, while 20% of data is taken as testing. Versus we'll declare random underscore state as any value 42, so that whenever we execute this command, the splitting happens in a same random fashion. So it's random, but it's controlled. Now, what is the deep learning architecture for this? Deep learning architecture for the simple training purposes is that we have X1 and X2 two features. These are from X underscore train. These both will be applied to the input. So how many neurons are required in the input layer? Two neurons are required. And then this will be connected to, suppose I'm using three hidden, just for demonstration, three hidden layers. The first hidden layer comprises of 1 to 64 neurons. So this is a fully connected layer. Remember, we use dense command. So fully connected just means that all the neurons of the input layer are connected to all the neurons of the hidden layer, which means these all are connected. I will use another hidden layer as hidden layer 2, and it comprises of say 32 neurons, and all of them are connected to the neurons in the previous hidden layer 1. And then finally, we use a hidden layer 3 that comprises suppose say of 60 neurons, and it is all of them are connected to the previous layer. Now these are my three hidden layers. The input is 2. What is the output? Output is the squaring operation. If the model understands, then it will predict the squared operation. So for that, the number of output layer will be 1. And how many neurons are required? 1, because the output is 1. And this neuron will be connected to all the previous hidden 3 neurons, all 16 of them. And the output will be, suppose y hat. So y hat is nothing else but an estimated, a predicted value of the trained model. So this is the architecture. How do I do this in Python? The model in Python will be firstly defined, then compiled, and then fitted. For the purpose of definition, we use a sequential model. Remember, we imported sequential. In the sequential, first of all, we'll use the dense. Dense means a fully connected layer. A layer will have an input and an output. So the input dimension is 2, which means there are 2 neurons. Why these are 2? Because these are X underscore train, and this will be X1, X2, the first two numbers. And the output will be 64. Why it is 64? Because remember, the output of the input layer is the hidden layer 1. So this is hidden layer 1, which comprises of 64 neurons. You got it right. The next definition is that we again use another dense layer comparison of 32, which what it is 32 is? This is the output of the dense layer, because the input of the second hidden layer is the output of the first hidden layer. The first hidden layer comprises of 64, so that automatically becomes here. You can also define input underscore dimension here as 64 from nothing when that's not required, because it automatically takes that. And this is the second hidden layer that has 32 neurons. And we also have a third hidden layer that has 16 neurons. Remember, in defining a neuron, we said that an activation of a neuron is required. So that activation is basically here for prediction purposes. We'll use ReLU. So all these layers are actually attempted using the activation function of ReLU. This is the activation function of each layer. What is the output? The output is consisting of one dense layer of one neuron, because the output is Y. So this is where this is very important that the input was 2 and the output is. In between you can play. Now what we can do is we can compile. For compiling, we use the name of the model. This name of the model we'll use here also, which means that this is going to be, suppose you write it DNN, then you can use DNN here, and you can use DNN.compile. This is user defined. What I'm trying to say, you can write your name, and that name can be used here. We use an optimizer. Generally for prediction purposes, we use Adam optimization, the loss based on which the weights and biases will be updated in each epoch is mean squared error. The metric is mean average error. The history, we'll try to plot the history, and therefore we will fit the model. The basic step is this. We want to save it in history. That's a different thing. But basic operation, after defining, compiling, we fit the model with X underscore train and Y underscore train. X underscore train is basically pre-processed X1 and X2. Y underscore train is 80% of Y, which is X1 into X2. We suppose train the model for 50 epochs. I discussed this in my previous lecture. 50 iterations in which weights and biases will be updated. Batch size is 10, which means in each epoch, 10 samples will be collected. So suppose in total there are 200 samples. So only 10 of the 200 will be taken, or the 100 will be taken. And you can understand if batch size is 10 and total number of samples is 100, there will be total of 10 batches, and each of 10 samples. Verbose one just means that whatever will happen at the output. We'll see how the program is compiling. But now this video lecture is about integrating machine learning. So what are the advantages when I integrate a machine learning model into this deep learning model? Traditional machine learning algorithms like decision trees, support vector machines, random forests are basically good for feature engineering. So if you have a lot of data that has a lot of features, before applying it to the deep learning model, you want to extract the features. It makes the complete overall system architecture more reliable and more efficient. We can make interpretability of the data better because the machine learning models will combine with deep learning models. So combining ML models will explain and validate the deep learning decisions. So suppose there is a feedback system, we can use it for a feedback system of deep learning models. What you are doing is correct or not? Yes. A hybrid modeling is better for performance because machine learning models are basically for simple and linear patterns, while deep learning models are for more complex and non-linear relationships. So if I integrate both, we combine both, we get a hybrid model, which will be better in performance. The data efficiency increases because we will have large number of labeled data. I will show this in this tutorial itself, how the number of features and levels increases. Other advantages like reduced computational cost is very important because when I use a machine learning model before a deep learning model, I am actually increasing the data set to train the model. So for now, the number of epochs can be reduced. And therefore, to achieve a certain mean square error, we can use less number of epochs, or in other words, if I fix the epochs, we will read in the same number of epochs, we will have less mean square error, a smaller mean square error when I use both ML and DL when compared to when using only one deep learning architecture. Enhanced generalization capabilities, a reduction in overfitting, versatility across applications for computer vision, natural language processing, wireless systems. So there are various advantages of integrating machine learning models into deep learning models. So how I'm going to do that in this present example? I'm going to use decision tree as my machine learning model. So at this machine learning model, I will train using the data set of X underscore train and Y underscore train, and then I will get an suppose that output is tree underscore print underscore train. So I will predict using X underscore train. I will predict using X underscore test, and I will augment the training data set, which means I will increase the number of features that I will give to the deep learning model using the predicted value from the machine learning model. So the training data set will now look like tree underscore print underscore train, which will be three in dimension, not two. It was X1 and X2 two before, but now there is an added output of the machine learning model. Similarly, I will use tree underscore patterns of test, which will be also of three. So now the input has three features. We'll now train the deep learning model. In block diagram representation, this means that the features which are X underscore train are X1 and X2. I will provide these two into the machine learning model. I'll use decision tree when use any. Decision tree will then give me tree underscore pred underscore track. This is the output, right? So what I will do, I will give this output also to my deep learning model apart from X1 and X2, which means now the number of inputs are X1, X2, and the output of the DCZ tree, which means I will use the same architecture, but what happens is now number of neurons in the input layer becomes three because there are three inputs, and I will use the remaining same first hidden layer 64 neurons, second hidden layer 32, third hidden layer 16, and I will just use one output to predict one neuron in the output layer to predict y hat, right? So this is an integration of machine learning with deep learning. Now we move on to how to do this in Python implementation. Python implementation of what we discussed just now.
So my file from where I am taking this is data underscore demo, and data underscore demo has these three columns: x1, x2, and y, as I discussed. X1 and x2 are values from 1 to 200, and y is basically multiplication of these values. So 2 into 2 is 4, 4 into 4 is 16, 5 into 5 is 25, which means y is basically x1 into x2, which is x square. So these are only 200 values as of now, so that the data set is smaller. I just want to demonstrate the concept, and then so I will first of all demonstrate how machine learning and deep learning models can be used for training this thing. For that, I'm using Spider uh, console IDE for, and where Python 3.7 I'm using. So here in this, as I discussed in the previous video also, if I run this, click this button, then the complete code is run. Or if I select a portion and click this, then the selection will run. So as I it is demonstrated, that will first of all import our libraries. So I will select this part and click this part. So here is the variable explorer where everything comes, and the console is there on the right bottom. So you can see that the various of Python libraries have been imported. Till now, in the variable explorer is empty. And now I will try to select this line df1, and I will click df1. So df1 is pd dot read underscore cav. My file name is data underscore demo. So when I run this, what happens is that the df1 data frame 200 comma 3, which means there are values which are from 0 to 199 are the indices, and the values are 200, 200, and this is 40,000, the multiplication, which means y x1, x2, and y I can import. But remember, what we want to do is that we want to create features and labels. So df2, if I only run this selection, you can understand now df2 data frame is created, which is x1 and x2, which are my x underscore train. I will make this. And similarly, my labels are only the second is indices. So df3 becomes this. So now I will make my features and labels by taking df2 dot values and df3 dot values in line number 16 and 17. I will just execute this portion. So my features are basically, uh, so in this way you can create your input, right? 1 into 1, 2 into 2, 3 into 3. This is my input, and my labels that I am presenting to the deep learning model are the squares. This is what I'm going to use for training. But as I said, that pre-processing is a major part, and therefore we'll use min-max scalar for scaling features and labels. What I will firstly perform is that I will make features. Features are actually the values from 1 to 200, but I want it to be between 0 to 1, so that the deep learning has to work only in that range. So when I run 19 and 20 only, you can see that now x scaled is there, and x scaled is also a value from 2 1 to 200, but now it is scaled, and the smallest value is 0, and the largest value is 1. So everything is scaled between 0 to 1. That is very important. Similarly, I will do it for labels also, because I want my y scaled to be only between 0 to 1. These are all those values which were from 1 to 40,000. Now, as I discussed in the video, that we will now uh, make x train, x test, y train, and y train using this test size, so that we can have our x train and y train. So this, if I run now, I have x train. You can understand x train will be 80% of the data. So these are 160 values, 0 to 159, and similarly y train will also be and corresponding levels, but 160, which are 80%. Why 80%? Because test size is zero point 0.2, which means testing data set will be 20% of everything, which is in this case 40. Now I will demonstrate this, that if decision tree is only used or machine learning is used, then how do we predict? So I define decision tree regression, because this is a prediction call object, as model underscore tree, and I will fit that on x train and ytrain, and I will perform prediction using the same name of the model, model underscore tree, but this time over text data. So now if I just select this decision tree and I execute this portion, you can now see that y, this is my important thing, that y prediction tree are the predicted values for 40, 0 to 39, which means the 40 test set that was there, right? This is the prediction using decision regression. Similarly, we can use support vector machine. So there is a concept of kernels, RBF I'm using. So if I again model underscore SVM is my support vector machine, I will fit the model using X underscore train and Y underscore train, and I will predict using SVM model, which is model underscore SVM dot predict over the test data set X underscore test. So if I perform this, I will have the predicted value using SVM, again 40 of them, right? I will compare later on what happens to when we do using deep learning. In deep learning, remember what I did. This is the name. Here I have changed the name because I want to demonstrate all three. So model underscore DL, sequential model, dense layer, activation function in ReLU, and the input side is 2 comma nothing. Why? Because my X train you can see is 160 comma 2. So 160 are the number of values, and we say that there are 160 values of dimensions 2 comma nothing, and therefore the input dimension is 2 comma nothing. And the output of the first layer is 64 because the hidden layer 1 is 64. I am just slightly changed. You can change this to, say, in my video as I discussed it was 32, and then I can also increase this to take, as I demonstrated in the video, to be 60. That always can be done. Now we have three hidden layers as discussed, and the output is one neuron. I will model underscore DL is the name. So what I will do, I will compile it for the given optimizer, and then I will fit over training and testing for suppose only 20 epochs, and I'm taking batch size to be 32. I can reduce the batch size, but it will take larger time. And then what I will perform, I will predict using this deep learning model, using model underscore DL, that is the name of the deep learning model, and dot predict over what? Over the testing data set. So if I now execute only this part, I will be able to get the output, right? So these are 20 epochs. You can see the mean square error is around 0.0021 right now. This is the loss, mean the loss 0.0021. And what are the values? The predicted values are this using deep learning model. If I increase the number of epochs, I will get better results. If I reduce the batch size, I will get better results, right? And I also want to now compare all three models. So I have already collected a data set. What I will now perform is that I will y underscore test and y underscore predicted. So what is the difference? What is the difference? And so I will use the mean underscore squared error function to calculate the mean square error and plot a histogram for decision tree, SVM, and deep learning here. So you can understand y underscore test is the testing levels, and y underscore predict is the predicted value using decision tree, using SPM, and using deep learning model. So if I just select this and run, you can see that now figures have come. So on this plot section, there is a figure, and you can see that the deep learning in 20 epochs is giving slightly more error compared to decision tree. SVM is performing poorly. The error, this is mean square error. So larger the error, worse is the system. So in this case, you can see that this performance of decision tree without anything is better. Since it's a normal thing, when I increase this to 50 epochs, you will see that deep learning overcomes this. Now, the concept that I have discussed, that we will integrate machine learning. So till this point, everything remains the same in this code. You know? Now what we will do, that I will run this. This is now the same thing, but I am just executed it again. And this time I'm using decision tree regression, and I will fit it over X underscore train and Y underscore train. And as I demonstrated, I will predict using X underscore train and X underscore train. So once I then run this part, we basically have tree underscore predict over testing data and training data. So you can see that this is the output of the system using decision tree. So this is one new feature that I have added. This is the new feature. And what I will now do, I will augment it into the original data set as I demonstrated. So this is the part in which now X underscore train underscore augmentation is basically X underscore train, what was already there, and the prediction of decision tree over the X train data, right? In line number 31. So when I run this, there is X underscore train underscore augmentation that has been created, and this augmented data dimensions is very important. This dimension is now 160,3, which means there are 160 values, but now three columns. The third has been generated using the machine learning algorithm of decision tree. Previously, The squaring operation had only two inputs. Now there are three inputs, 160 of them and three. We also want to test it. So we will also create an augmented test data set. So this is tree underscore x underscore test underscore augmented data, and this will be 40 comma 3. This is training and this is testing. So here it is 40 comma 3. And now I will perform my deep learning. I will again change this dimension as the architecture I demonstrated. So I will take it to be say 32, and this to be 16, and I'm still running everything. But now the input shape has become 3 comma nothing, right? It's very easy to understand, because now that x underscore train underscore augmented, over which will fit, is having three features, and the labels are still one. So in this way, if I now run again for only 20 epochs, and batch size is also same, and if I run now after this part, if I run, so you can see the performance of the deep learning model, and you can see the mean square error. The mean square error previously was 0.02, if you remember. Now it has come to an order of 10 to the power minus 4. This is only because you have increased the input dimensions. And using the input dimensions, when I have increased, the performance of the model has become better. I can also perform inverse transform to take the original scaled value to being unscaled, which means we will get 40 values to be the square of the input, and I can predict using any other input data set. But my main focus in this video lecture is that now we can integrate machine learning with deep learning to make a system more reliable. So in this video, we have also demonstrated the simple deep learning model.
Thank you for watching this video. Do like and subscribe to the channel so that I am supported and I continue to create such contents. Thank you so much.